All right, so this is chapter 12, which is all about gases. And this PowerPoint itself might differ a little bit from the book material in terms of where everything is ordered and things like that. So I just wanted to let you know that. All right, so when we think about gases, we really need to be thinking about kind of the pressure and what gas does in terms of pressure. And so we've known about air for a very long time. It was considered one of the four fundamental elements way back in the day. And then in the 18th century, they figured out that air is actually a mixture of gases. It's a lot of bit of nitrogen, a little bit of oxygen, some carbon dioxide. Some of our noble gases are up there, water vapor, that sort of thing. Where you might have heard about air in the news, we had ozone depletion up in the atmosphere. It was more so the late 90s, early thousands, but we're starting to get it back. And then you've also probably heard of carbon dioxide and global warming. So when we think about gas pressure, we really should be thinking about atmospheric pressure. And it's weird to think about, but all the air above us is being pulled down to the earth with gravity. And so even though it's free floating above us, it still has a mass to it. And so it's being pulled straight down to us and provides a pressure above us. Uh, if we were at sea level, the pressure at sea level is 14.7 pounds of pressure per 1 square inch. Now, our bodies have developed so that we can handle that amount of pressure. And then as we go up in the atmosphere, we go down in pressure because there's less air above us. So when you're up on a mountain, the pressure is a lot lower because there's less air above us. So the definition of pressure is the force exerted on a given area, and gas pressure results from the force provided by molecules colliding with the surface of objects. So providing with the surface of a balloon, with a tire, with our bodies in the air, that all exerts a pressure. Now, the English system unit for pressure is PSI, which you might have heard for your tires. Typically, we inflate our tires to around 35 PSI-ish. So you've probably heard of that. And a mercury barometer is the device used to measure atmospheric pressure. So some other units would be millimeters of mercury. That's what we use with that mercury barometer. So that unit there literally stands for millimeters of mercury. And I'll show you a picture of a barometer here in a bit. Essentially what happens is that the atmospheric pressure pushes down on a cup of mercury, and then it forces up into a tube where we can measure it. The most common unit of gas pressure is the atmosphere, an ATM. And 1 ATM is considered normal atmospheric pressure, which would be kind of our normal standard atmospheric pressure just at sea level. And then the conversion factors that are provided on your exam sheet are the following. So 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr. Torr is just another unit, and torrs and millimeters of mercury are equal to each other. So we use a barometer to measure atmospheric pressure, and so the atmosphere exerts a force down into kind of like a cup, and then that mercury is forced up into a tube with a measurement of millimeters on it, and we're able to measure the exact pressure. Now, again, pressure varies depending on the day, the time, depending on the weather, depending on how high up we are in the atmosphere, so it all changes. So here's what it looks like. You can see those purple arrows on the outside. That's the atmospheric pressure just pushing down into that bowl. And the reason we use mercury is because mercury climbs far less than water. And so if we wanted to use a water barometer instead of mercury, our water barometer would have to be 34 feet high, versus a mercury barometer only has to be about 2.5 to 3 feet high. So we use the mercury barometer because the mercury moves a lot less based on the change in atmospheric pressure. So we have to think about a few gas laws here. Now, with the gas laws in your book and in this slideshow, you'll see the names of the guys who have the gas laws. I'm not going to require that you memorize the names of the guys. I would like you just to memorize the relationships and why that kind of happens. So there's many different types of gases. We've got elements as gases. We've got our noble gases. We've got our diatomic gases. We also have compounds that are gases: carbon dioxide, carbon monoxide, water, ammonia. So those are all examples of just compounds that are gases. And then all gases are dependent on the same four properties: volume, the amount of gas, the temperature, and the pressure. So the first one I'll talk about is Avogadro's law. This talks about the volume and the amount of gas. And so the volume of a gas is directly proportional to its amount. When you see the word directly, when we think about that in terms of math, directly means that as we go up in one thing, the other thing also goes up. Or if we go down in one thing, the other thing goes down. So if we increase the amount of gas, the amount is N. N stands for moles. Okay, moles is an amount. So as we increase the moles, we also increase the volume. That's what directly means there. So K, you'll see it on the next few slides. K is just a constant, meaning that never changes. And so we kind of eliminate that, and then we can set them equal to each other. So the volume is directly related to the amount. And so we think about that in terms of kind of like a basketball pump over there. If we want to inflate the volume of the basketball, we've got to put more moles of gas by using that pump. The next one is temperature, or when we think about using temperature in our gas laws, we need to use Kelvin. And the reason we need to use that is because Kelvin doesn't have any negative numbers, and that's because 0 Kelvin, the temperature of 0 Kelvin, is when all atomic motion stops. So it's so cold that all atomic motion stops. There's no way to get negative numbers. And we can't have negative numbers in these calculations, so we have to always be using Kelvin in any of our calculations. So to go from degrees Celsius to Kelvin, we need to add 273. And so when we add 273, typically we're just going to go to the ones place for the most part. So 23 degrees now becomes 296 Kelvin. The next one would be pressure and temperature. So if we keep the volume and the amount of moles of gas constant, and we're only looking at the relationship between pressure and temperature, they are directly related. And the way that I always think about this one is an Instapot. So what happens in an Instapot is you close off the lid, so it seals the volume and it seals the amount of gas that's in there. And then what happens is that pot increases its temperature. So when it increases its temperature, its pressure also increases, which also kind of increases the temperature again. So I always think about the Instapot. Increasing temperature is what causes the pressure to build up. And so the pressure of the starting over the temperature of the starting equals the pressure of the new over temperature of a new. So we're going to be using these equations on the bottom quite a bit. And so P1 and T1 just mean the initial conditions, and P2, T2 just mean the final conditions or the second condition. So anytime you see a 1 or a 2, the 1 means kind of an initial, and the 2 means a final. And you could be solving for any of those 4 variables. You always need to know 3 of them, and 1 needs to be unknown. Next is Charles' law, which talks about volume and temperature. So this one, if we think about it in terms of real life, if you were to go into Party City and get a nice balloon, and then you take it outside and it's freezing cold outside, what you'll probably notice is that your balloon looks something like it does on the right, a little deflated, not as filled as it should look. And that's because the temperature has decreased, which means that the molecules aren't moving around as fast, which means that the volume also decreases. And so you can see it also down there in the bottom corner. Hot water makes the balloon shrink. Those particles aren't moving around as much, which decreases the volume. And then the last one is Boyle's law, which is volume and pressure. So the volume of a gas is inversely proportional to its pressure. This is the one law that is not directly. So the other 3 were direct, meaning as you increase one thing, it increases the other. So increasing temperature increases pressure. increasing temperature increases the volume, that sort of thing. This one is the one that's inverse. And what that means is that as we increase one thing, the other thing decreases, or if we decrease one thing, the other thing increases. And so for this one, my example to you is this scuba diver. And you might have heard of the bends. The bends are what happens when you scuba dive and you come up to the surface of the water too fast. So when you're down deep in the ocean or wherever you're scuba diving, there's a lot more pressure on you. The water above you is pushing down on you, and so there's a lot more pressure. That means that the volume that the gas within your bloodstream takes is a lot lower. And then as you come back up to the surface, the pressure becomes lower, meaning the volume of gases within your blood becomes higher. And so what the bends are is when you come back up to the surface too fast, it's typically the nitrogen in your blood increases volume too high, and then it makes you sick and you could pass out. So this one, also, you can think of kind of being on a mountain. So if you were to take a balloon at the bottom of a mountain and just blow it up a little bit and then take it to the top of the mountain, at the top of the mountain, there's a lot less pressure. And so it should have a higher volume when it gets up to the top. If you were to blow a balloon up to like a normal size at the top of a mountain and then go down to the bottom of the mountain, the balloon size should shrink because the bottom of the mountain has more pressure, which means the volume should be lower. So we can put it all together in what's known as the combined gas law. So this equation down there is on your exam reference sheet, and it's P1 V1 over T1 equals P2 V2 over T2. Now, you don't always have to have all six things. The nice thing about this equation is that you can break it down. So let's say that you don't want to be dealing with all of these different all those different variables. You can just use the ones you need. So to use the combined gas law, you can figure out if a variable is staying constant. So if we're keeping volume, pressure, or temperature constant, then you can cross it off the equation and not deal with it. Then you can only deal with the two other variables there, either pressure, temperature, or volume. Now, sometimes you will have to deal with all three, which means that you'll be given 5 pieces of data and 1 unknown. Other times you'll be given 3 pieces of data and 1 unknown. When that's the case, you'll be able to cross off a variable. My next piece of advice would be to make a list of the data from the problem and which variable they represent. Do they represent P1, V1, T1, or P2, V2, T2? And you can kind of figure that out by reading it. So again, the ones mean it's an initial. The twos mean it's kind of a final condition. P is pressure, V is volume, and T is temperature. My advice is to put a question mark by the variable you are trying to solve for. So if we're trying to solve for V1, put a question mark by that. Then I would use algebra to solve for the unknown variable. Again, if you can cross off a variable type, let's say P, V, or T, cross it off right away, and then solve for that unknown variable, the variable you put a question mark by. Make sure that all the units in the data list match, meaning make sure that you have the same units. They could be milliliters or liters. It really doesn't matter there. It could be millimeters of mercury, torr, or atmospheres. It really doesn't matter what units you use for this one, but you always want to make sure that they match up. Make sure that your temperature is always in Kelvin. We need to use Kelvin for this entire gas unit. And then as long as you've rearranged your equation using algebra, you can plug in your units from the list and solve. So again, sometimes you don't have to use all 3 of the variables. Sometimes you just need to use 2 of them. So if we want to keep temperature constant, we're going to just deal with the pressure and the volume. So P1 V1 equals P2 V2. If we want to keep the pressure constant, we're just going to be dealing with volume and temperature. So V over T equals V2 over T2. And then keeping volume constant, we're just going to be dealing with P1 over T1 equals P2 over T2. You don't need to memorize those. Again, you'll be given the one in white up at the top, and you just need to know, okay, if I'm only dealing with 2 things, I can cross off the other thing, and then you'll have to be able to rearrange it. So here's a gas law example. A 3-liter container has a pressure of 5 atmospheres. What is the volume if the pressure of the container is 2 atmospheres? So we're not using T, so we won't have to use that version of the equation. And then you can see my list there. My P1, my initial pressure was 5 atmospheres. My initial volume was 3 liters. And then my final pressure was 2 atmospheres. I'm trying to solve for V2. So you can see over there I do a little bit of algebra. I divide both sides by P2 to get V2 all by itself. So V2 is equal to P1 V1 over P2. And then you can see me plug in my numbers and I cancel my unit to get liters. So I want you to figure this one out. A constant volume container has a pressure of 2.5 atmospheres at 25 degrees Celsius. What is the pressure at 45 degrees Celsius? So convert your temperatures to Kelvin. Again, add 273. Make your list. Then solve for that unknown. All right, so we're not using volume here. So P1 is 2.5 atmospheres. T1 in Kelvin is 298. I do not know P2, so that's what I'm going to be solving for. And T2 is 318 Kelvin. So for this one, I'm going to multiply each side by T2 to get it off of the bottom of the P2 side. So my P2 is equal to P1 T2 over T1. Plugging everything in, I have 2.5 atmospheres times 318 Kelvin divided by 219 Kelvin, and my new pressure is 2.7 atmospheres. That should make sense because if I increased my temperature, my pressure should also increase. All right, now this one you're going to have to solve for just one unknown. So when you fill a typical scuba tank with air, it has a volume of 13.2 liters and a pressure of 153 atmospheres. If the water temperature is 27 degrees Celsius, our question is asking how many liters of air will a tank provide to a diver's lungs? The body temperature of the lungs are 37 degrees Celsius. At a depth of 70 feet in the ocean, that's just irrelevant, where the pressure is 3.13 atmospheres. So you're solving for V2. So figure out what all the ones are, and then P2 and T2 are. Rearrange for V2, and then plug in your numbers. Make sure that your temperatures are in Kelvin. All right, so there's my list on the side. I start with 153 atmospheres in a 13.2 liter tank at 300 Kelvin. And then my new pressure is 3.13 atmospheres. My volume is what I'm trying to find, and my new temperature is 310 Kelvin. So if I rearrange for V2, I need to multiply it by T2 over P2. Again, that's to cancel out P2 and my T2. So V2 is equal to P1 V1 T2 over T1 P2. Now, it does not matter what order those things come in. That's just the way that I do it. And then I plug my numbers in. I cancel out my atmospheres. I cancel out my Kelvin. And so I'm left with liters. So that tank of air in the scuba tank would provide my lungs with 667 liters of air. Now let's talk about the kinetic molecular theory, which is just the kind of the list of rules that define the way that gases interact with the world around us. So gases are composed of molecules that are in continuous motion. They travel in straight lines and change direction only when they collide with other molecules or the walls of the container. The molecules composing the gas are so small compared to the distance between them. The pressure exerted by gas in a container results from the collisions between the gas molecules and the container walls. Gas molecules exert no attractive or repulsive forces on each other. So what that means is they aren't attracted to each other and they aren't repulsed by each other. They're just bouncing around randomly. And then the average kinetic energy of the gas molecules is proportional to the Kelvin temperature of the gas. Why am I talking about this now? Because this set of rules is how we're going to think about gases when we talk about our next law. So we like to think about this being the true case. In reality, our gases sometimes don't exhibit these rules. Sometimes they do have a little bit of attractive or repulsive forces, but for the most part, we're going to think about these as our rules. So how does this affect our gas laws that we just learned about? Well, that first picture there, if we were to increase the temperature of the container but keep the volume constant, our pressure should increase. That's because our particles are moving around faster. When they move around faster, they hit the wall more often. When they hit the wall more often, you have a higher pressure. The next one, if we decrease the volume but keep the amount of particles in there the same, then when we decrease the volume, our pressure is also going to increase. And the reason for that is because we decrease the space that those particles can bounce around in, so they have to hit the wall more often, which increases the pressure. And then the last one, if we increase the amount of gas that is in a container, our volume is going to want to increase. And the reason for that is because we'd like to maintain a constant pressure. The gases don't want to be colliding around as much as they have to. So if they can increase the volume, they would increase the volume. So we use those sets of rules to think about the ideal gas law. And the ideal gas law puts everything together. It puts pressure, volume, the amount of gas, and the temperature all together. Now, this equation is on our exam sheet. You just need to know what the variables are and what units they need to be in. So P is pressure, and it needs to be in atmospheres. So if you're ever given a problem with it in millimeters of mercury or torr, you're going to have to get it to atmospheres. Again, remember, 1 atmosphere equals 760 millimeters of mercury or 760 torr. So you can convert between the two there. Volume has to be in liters. So if it's in milliliters, you've got to get it into liters. N has to be moles. If you were given grams, you're going to have to get it into moles. T is temperature in Kelvin. Your temperatures for the whole gas unit always need to be in Kelvin. And then R is the ideal gas constant. This gas constant is also on your equation sheet, so you don't have to memorize that. Its value is 0.08206, and the units on there are liters times atmospheres over moles times Kelvin. If you can't remember what units need to be used in this equation, always look down here in the units attached to this number. Your volume needs to be in liters. Your pressure needs to be in atmospheres. Your moles, N, need to be in, or your amount needs to be in moles. And then our temperature needs to be in Kelvin. So if you can't remember what units you need to be in, take a look at your R constant there. So if we have different units with the ideal gas law, here's how we can go about changing them. So pressure could be given in millimeters of mercury or torr. We're going to have to get it out of those units and into atmospheres. So remember, 1 atmosphere equals 760 millimeters of mercury and 760 torr. The volume could be given in milliliters. You just have to convert it to liters. Remember, there's 1,000 milliliters in a liter. Your amount could be given in grams, which needs to be converted to moles. So you're going to use the molar mass of the substance to go from mass to moles. And then temperatures are typically given in degrees Celsius. You need to take it and get it into Kelvin. So here's an example. How many moles of gas are there in 2.35 liter sample that is at 6.75 atmospheres and 54 degrees Celsius? So what I'm going to do here is my pressure is 675 atmospheres. My volume is 2.35 liters. I do not know my moles. You always know your R. Your R is always known. It's always that 0.08206 atmospheres, liters over moles, Kelvin. And then our temperature we have to take to Kelvin. So 54 is 327. Now, I always rearrange my equation to solve for the one variable that I have my question mark by. So solving using algebra, I'm going to divide each side by RT to get it off of the left side or the right side. So my N value is PV over RT. Plugging my values in. If we take a look here at how units cancel, I cancel out my atmospheres. I cancel out my liters. I cancel out my Kelvin. And I'm just left with moles, which gives me the answer that I need there. So, methane is being considered for use as an alternative automotive fuel to replace gasoline. 1 gallon of gasoline could be replaced by 655 grams of methane. What is the volume of this much methane at 25 degrees Celsius and 745 torr? So determine the number of moles in the sample. You're going to have to do that by a little bit of molar mass math. Then you're going to convert the temperature to Kelvin, convert the torrs to atmospheres, rearrange your ideal gas law to solve for volume, and then plug those values in. So this is what it looks like. Our moles, we're taking 755 divided by the molar mass of 16.04. So we get 1 mole, we get 40.8 moles total are in that sample. Our temperature is 298 Kelvin. My pressure is 0.980 atmospheres. And so when I rearrange my equation for volume, I get nRT over P. So my moles cancel, my kelvins cancel, my atmospheres cancel, and I'm left over with liters. So if we take a look and think about why we would maybe not use methane as a new fuel, it would be because for 1 gallon of gas, you would need 1,020 liters of space. And that's just an insane amount of room that you would need in a car to have this new type of gas. We can also calculate the molar mass of a gas. So the molar mass of the gas can be used by finding the following. This is on your equation sheet, so there's no need to memorize this. You just need to know the different values. G is grams. R is still the gas constant, 0.08206 atmospheres liters over moles Kelvin. T is temperature in Kelvin. P is pressure in atmospheres. And V is volume in liters. So it's pretty straightforward for the most part. You just go ahead, plug in your numbers, and solve for the answer. So an unknown noble gas with a mass of 6.52 grams is in a 1,780 milliliters container with a pressure of 3,374 millimeters of mercury. The container is at 25 degrees Celsius. What is the molar mass, and identify that molar noble gas? So you need to make a list of the data with correct units. Remember, you need liters, you need atmospheres, and you need Kelvin. So you're going to have to do a little bit of math first to get those units to what they should be. Then you can plug all the values in, solve for the molar mass, and then you can figure out what noble gas it is. So my grams would be 6.52. My temperature is 298 Kelvin. My pressure is 4.44 atmospheres. I got that by taking my millimeters of mercury divided by 760. And then my volume is really 1.78 liters. So I took 1,780 divided by 1,000 to get 1.78. I plug all my values in. I'm left with just grams and moles. So my molar mass here is 20.17 grams per mole, and that is almost exactly what neon is. We can also find the density of gases. So density does not depend on the amount of substance. It just depends on what substance we have. And so to figure this out, we've got the pressure times the molar mass of that substance over the R value times our temperature. So pressure needs to be in atmospheres, molar mass. Remember, if we have a diatomic gas, so hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or not bromine, but those ones, hydrogen, nitrogen, oxygen, fluorine, and chlorine, you need to double their masses from the periodic table because they exist as a pair. And then our R value is always the same, and temperature still always needs to be in Kelvin. All right, so this question asks, what is the density of molecular nitrogen gas at 273 Kelvin and 1 atmosphere? So remember that nitrogen is a diatomic element when you go to solve for this. But otherwise, you should be able to pretty much plug everything into that equation and get an answer. All right, so the molar mass of molecular nitrogen is 28.01 grams per mole. When we substitute that in along with our 1 atmosphere and 273 Kelvin, I get a density of 1.25 grams per liter. So that's the units that your density is going to come out to. We get that by canceling out some units. So if I take a look here, I get grams per mole in my units of molar mass. So mole cancels out there. Kelvin cancels out. Atmospheres cancels out. And so I'm left with grams over liters, which looks something like that. All right. The next thing we're going to talk about is Dalton's law. Dalton's law says that the total pressure of a system is equal to the pressure of all the gases combined. So what this general equation is saying is that the total pressure of a gas mixture is equal to the pressure from gas A plus the pressure of gas B plus the pressure of gas C. Now, each pressure exerted by an individual gas is what we call the partial pressure. Now, this is kind of what it looks like if I took 300 kilopascals. A kilopascal is just another unit of pressure, okay? So it's just like an atmosphere or a millimeter of mercury, that sort of thing. So if I take 300 kilopascals plus 450 kilopascals plus 600 kilopascals and add them all together, my total combined pressure from those three substances combined is 1,350. I just added those three together to get that. Now, why do we care about this? The biggest reason is when we go to do lab, typically we collect gas over water, meaning that we fill a container up with water, we flip it over. When we flip it over, then we have gas in the container, and then we have water in the container, and then any gas that we collect bubbles up through the water and then pushes that water out towards the bottom. Now, when the bubbles come up through the water surface, it takes some of that water and turns it into water vapor, which has a little bit of pressure. And so we can think about the total pressure, the PT, of the system is equal to the atmospheric pressure, and then the pressure inside that container, whatever we're measuring it with, is equal to the pressure of the gas that we're thinking about, but also the pressure of water vapor. So this is kind of what it looks like. You've got your reaction producing gas, and then it's bubbling up through the water. Now, up in this gas up in the top here, this gas up here contains the gas from the reaction, but it also contains water vapor. And so the total pressure, PT, comes from the atmospheric pressure pushing down and up into the flask. And so PT is our atmospheric. And then the pressure inside here is equal to the pressure of our gas that we're looking at plus the pressure of water. So this is kind of what we think about when we collect gas over water. Our pressure of our total is atmospheric. Pressure of water is the pressure from the water vapor. And then in this case, this is just talking about if we're collecting hydrogen gas, it would be the pressure of hydrogen gas. So how do we figure out the pressure of water vapor? Well, there is technically a graph. A lot of times you'll get a table. And so we just have to measure the temperature of the water that it's being collected in. And then the temperature of that water gives us whatever pressure it is. And so let's say that the pressure or the temperature was like 25 degrees Celsius. Our water vapor pressure is not very high. It's somewhere around maybe 30 torr. So usually our water vapor pressure is not very high. Now, if we want to do partial pressures math, let's say we're trying to find the total pressure. We would need to know all the partial pressures from all the gases, and we just add them up. Let's say we're trying to find the pressure of just one gas. You're going to solve for that one gas by taking the total pressure minus the other pressures of the gas. All right, so here's some sample problems. Number one, a 10-liter vessel contains 0.0850 atmospheres of neon, 437 torrs of nitrogen, and 9.5 millimeters of mercury of xenon. What is the total pressure in atmospheres? Here you're going to have to do a little bit of conversion to get us 2 units of atmosphere so that we can add them up. And then number two, a burette, which is just a collection container that we use in lab, is filled with air and water vapor. The total pressure of that that burette is 755 millimeters of mercury, and that's at 25 degrees Celsius. The pressure of the water vapor is 24 millimeters of mercury. And so what is the pressure of the air in the burette? So that one is an example of just like collecting the gas over water. All right, so the first one, we had to get to all units of atmospheres. And so we take the 437 torr divided by 760 to get us 0.7575 atmospheres. And then 9.5 millimeters of mercury is really 0.0125 atmospheres. We add those all together and we get 0.673 atmospheres is our total pressure there. And then for the second one there, we're solving for the pressure of just the air that was collected. And so we are taking the total pressure, which was that atmospheric pressure, and then subtracting it by the water vapor pressure. So we get 731 millimeters of mercury was just for the pressure of the gas, the air. All right, the last thing we have to talk about is stoichiometry in gaseous reactions. So gases can appear as reactants or products in chemical reactions. We can use the ideal gas law, the balanced chemical equation, to be able to relate the different things to each other. And the stoichiometric factors, meaning our mole-to-mole ratios, can be used as well. So this is what we're kind of thinking about here. We're going to be dealing with grams, moles, and liters of gas. Sometimes we are at STP and other times we are not at STP. I'll have to talk you through what STP actually is here in just a sec. And then we will be able to go through this whole map by the end of the lecture. All right, so we have what is called standard temperature and pressure. And so in these standard conditions, these are the temperatures and the pressures that we consider kind of standard for gases. So it would be 0 degrees Celsius, which is equal to 273 Kelvin, and 1 atmosphere or 760 millimeters of mercury. So why do we care about this? Because at STP, the volume of 1 mole of any gas is 22.4 liters. So no matter if we've got helium, ammonia, or oxygen, all of those are going to contain about 22.4 liters of gas. So what this allows us to do is it allows us to add another conversion to our toolbox. We can use this 22.4 liters of gas per 1 mole of gas in one of two ways. Now, you will need to memorize this conversion because it'll save you a lot of time in these different math problems. So if you see that the problem says STP for a stoich problem, then try to use this 22.4 liters of gas. Again, you may need to have liters on top or bottom, but it's important to remember that the 22.4 always goes with 1 mole. Now, if the problem's not at STP conditions, we will have to use a little bit of Pivnert, our ideal. All right, so here's a problem with this. We are going to be starting with, we're going to be dealing with STP first, and then we'll go to non-STP conditions in a little bit. So this problem explicitly states that we're at STP in the problem, and it states that how many grams of ammonia are produced if 15 liters of nitrogen are reacted with excess hydrogen. So we've got the 15 liters of nitrogen, we've got more than enough hydrogen. We're trying to figure out how many grams of ammonia. So we're going to start here with liters of nitrogen. Then we can go to moles of nitrogen. Then we can go to moles of ammonia, and then finally into grams of ammonia. So to figure this out, I'm going to take my 15 liters of nitrogen. I'm going to then get out of liters of nitrogen into moles using that 22.4. Then I'll use my mole ratio of 1 to 2. And then finally the molar mass. 17.04 came from 1 nitrogen and 3 hydrogens. This next one, how many liters of hydrogen are needed to react with nitrogen to make 76.5 grams of ammonia at STP? So again, we're at STP. I'm going to start with grams of ammonia because that's what was given in the problem. The only place to go from there is moles of ammonia, then to moles of hydrogen, then finally into liters of hydrogen. So I'm going to start here with grams of ammonia. Again, my molar mass hasn't changed since that last problem. So out of grams into moles. Then I use my mole ratio of 2 to 3, and then I get out of moles and into liters using that 22.4 liters. And lastly, if I want to go between liters, here what I can do is I can use that 22.4, but I'll show you a little trick here as well. So we're going to start with liters of nitrogen, go to moles of nitrogen, to moles of hydrogen, to liters of hydrogen. So if we use the 22.4 liters here, what I want you to notice is that you're going to see that number appear on the top and on the bottom. So technically they act each other. And so what I can do is technically, if I am going from liters to liters and it's at STP, technically here what I can do is I can just use the mole ratio to get between them. But I think it's sometimes helpful just to do the method that we always use so that you don't get yourself confused. All right, so balance the following equation and then answer the following question. So we're dealing here with iron reacting with oxygen to form iron 3 oxide. And we're trying to figure out how many grams of iron are needed to react with 8 liters of oxygen at STP, and how many liters of oxygen are needed to produce 30 grams of iron oxide at STP. All right, so to balance this, I need a 2 in front of this. I need a 3 here, which means I need a 4 here. And then to take a look at my work, you're going to see my mole maps within my work. So I start here with liters of oxygen. I then go to moles of oxygen, then to moles of iron, and then into grams of iron. And so here I start with 8 liters, get it out of 8 liters and into moles using that 22.4. Then I use my mole ratio 3 to 4, and then I use my molar mass from moles to grams. Then for the next one, I'm starting with grams of iron 2 oxide, going into moles using my molar mass, then going into moles of oxygen using my mole ratio, and then using the 22.4 to go back into liters. So here I'm starting with 30 grams of iron oxide. I figured out my molar mass by taking 2 iron masses plus 3 oxygen masses. I get my mole ratio from my coefficients up above, and then I use that 22.4 liters per 1 mole to get me back into volume. All right. So if we are not using STP, if we're not in STP, then we have to use PivNert. Okay. So if we were given a volume of a gas and we're not at STP, what we're going to do is we're going to start with PivNert, and we're going to solve for our N. So we know our pressure, we know our volume, we know our R value always, and we'll know our temperature. We're trying to solve for that that N, that moles. Once we have that N value, then we can continue in a stoichiometric problem to be able to get to our final answer. So this one is asking how many grams of water are produced if 2 liters of hydrogen gas are reacted in excess oxygen at 1.5 atmospheres and 27 degrees Celsius. So you can see here we're not at STP, which is 1 atmosphere and 0 degrees Celsius. So here we're going to start with our PivNert, solving for that N. So our N value comes out to 0.1827 moles of hydrogen gas. Then we're going to take that value there, and we're going to start a stoichiometric problem. We need to go from moles of hydrogen into moles of water, and then from moles of water into grams of water using our molar mass. So here we start with PivNert because our conditions are not STP, so we can't use that 22.4 anymore. So start with PivNert to solve for N. N, remember, is moles. So we get moles out of there. Then we start our stoichiometric problem with that. And our stoichiometric problem can be normal after that. So we have moles of hydrogen gas getting into moles of water, and then from moles of water into grams of water using our molar mass. So balance the following equation and then answer the following questions. How many grams of water are produced if 15 liters of C2H4 are combusted at 775 millimeters of mercury and 23 degrees Celsius? So remember to get to the correct units in order to be able to use PivNert here. And then you should be able to start with PivNert, get the moles of C2H4, and then make your way over to grams of water. All right, so if we take a look at what we need to do to balance this, we need a 2 in front of carbon dioxide. We need a 2 over here in front of water, which gives us 6 oxygens on that side, so we need a 3 here. Now, if we take a look at our work, we need to convert our pressure from millimeters of mercury into atmospheres. And so we take 775 divided by 760, and that comes out to 1.02. And then our 23 degrees Celsius really equals 296 Kelvin. So again, I'm going to solve for that N. So N equals PV over RT. We have 1.02 atmospheres times 15 liters, and then divided by our R value times 296 Kelvin. So I really have 0.630 moles of that C2H4. Then I'm going to start with that as the start of my stoichiometric problem, get out of moles of C2H4 into moles of oxygen, and then, that's supposed to be water, not oxygen. And then out of moles of oxygen or water into grams of water. And so here we get 22.7 grams of water. So again, we started here with our Pivnert equation. We had to get our units out of millimeters of mercury into atmospheres, and then out of degrees Celsius into Kelvin. Solving for the N, I get 0.63. And then we do a little bit of stoich. We get out of moles of C2H3 into moles of water, and then out of moles of water into grams of water using the molar mass. All right, so let's say that we are trying to solve for volume not at STP. In this sort of problem, we would probably be starting with grams of a substance, and then it would be asking us for liters at the very end. And so we would start with a stoichiometric problem just like normal to be able to get to moles of the gas that I care about. And then we're going to use that moles in Pivnert to solve for volume. And so in this case, what is the volume of hydrogen gas produced if 10.5 grams of aluminum reacts with excess hydrogen or excess hydrochloric acid at 20 degrees Celsius? So here we are going to be starting with grams of aluminum. That was what's given to us. We want to get to moles of hydrogen so that we can use that moles in our Pivnert equation to solve for V. Remember that the moles is N within that equation. So I start with 10.5 grams of aluminum, get out of grams of aluminum into moles using my molar mass, and then I use my mole to mole ratio. There's 2 moles of aluminum per 3 moles of hydrogen in this equation, and so I get 0.58376 moles of hydrogen. I'm then going to reuse that value as my N within Pivnert. So I'm solving for V. I have 293 Kelvin. I got that from taking 273 plus 20, and then I get 1.1 atmosphere from my problem. So this reaction here would create 12.8 liters of hydrogen. So I want you to balance the following equation and then answer the following questions. I'm reacting aluminum with sulfuric acid to create aluminum sulfate and hydrogen gas, very similar to the last one. How many liters of hydrogen gas are produced if 16.25 grams of aluminum react with sulfuric acid at 1.5 atmospheres and 35 degrees Celsius? All right, so if I take a look at what needs to be balanced here, I need 3 of my sulfuric acids, I need 2 aluminums, and then I need 3 hydrogen gases over here. If I take a look at my work, I'm going to start with a stoichiometric problem. Then I'm going to end in Pivnert. So here I convert my degrees Celsius into Kelvin. I just do that first just to get it done. But then I'm going to start with my 16.25 grams of aluminum. I'm going to get out of grams of aluminum into moles of aluminum, out of moles of aluminum into moles of hydrogen gas. And so that's going to equal 0.9034 moles of hydrogen. Again, that's my N value in Pivnert. I'm solving here for volume. So reuse that moles value times our R value times our temperature divided by our pressure. And so this would produce 15.2 liters of hydrogen gas. All right.
what volume of hydrogen at 27 degrees Celsius and 723 torr may be prepared by the reaction of 8.8 grams of gallium with an excess of hydrochloric acid? So this one here, convert your grams of gallium to moles of hydrogen, convert that temperature to Kelvin and the pressure to atmospheres, and then use the ideal gas law with the above information to find out your volume. All right, and the last thing we need to talk about is just limiting and excess reactant problems that can be done with gases. So the process does not change, except you may need to use the methods that we've figured out before this to find your answer. So always figure out what unit and substance you need to go to in your limiting reactant problem. You can run 2 stoichiometry problems that get you to the product in the unit. Use that 22.4 liters per mole for STP and use PivNert for non-STP conditions. So please don't let that situation screw you up. You're just going to do your stoich just like we always have. Always get to the same unit and same substance that the problem is asking us for, and then you go backwards to solve for your excess reactant. And then here's just kind of a look at the volume ratios again. If we react the volumes, 1 volume of nitrogen combines with 3 volumes of hydrogen to form 2 volumes of nitrogen. If we're at constant temperature and pressure, we can technically use the coefficients as ratios as well.